today I'm going to try to cover a lot. So let's see if we can do that. So first I'm going to finish with the discussion of hopefully GPT, and then talk a little bit about the other way of doing nonlinear feature or nonlinear classification or regression, and then a little bit about regularization and this ridge regression or the ridge penalty that we've seen in our problem multiple times. So I'm going to sketch the theory. You don't have time to talk about too much of that, but there's a chapter in the book which I'm going to update, and you should be able to follow. Okay, so we were talking about these ideas of language modeling, and the main point is that although they look like the results look very impressive, at the heart of these models is this supervised learning problem. So you're trying to predict the next word in the context, which falls within the settings that we have been discussing. Okay, so it's very natural classification problem, multi-class classification, except that, for example, the context is large, and you wouldn't be able to do a good prediction if you just try to model it as like a discrete feature with say 65 to the 8 levels. So that's not going to work that well. We saw the bigram language model, and you saw the results. So this is, for example, with at initialization. So this is the output that you produce, and this is after we train, and it looks better. So, but it's still not quite it's far from impressive. Okay, you get the sentences right, sort of line spaces. It looks like a text, but in a closer inspection, there's not much going on. And so this is a plot of the training loss versus the validation loss. So training, if you want risk, and this is the training risk. Usually they call it loss, but it's really an average, so expectation. And you can see that it pretty much matched training and validation, and you quickly converge, and there's like a final value of 2.4. So there's a few first iterations. Like this is like 300. You have a huge drop, and then very gradually flatten out. Okay, and the fact that they match is sort of suggests that the model is not too complex, so you're not overfitting. We'll see an example of overfitting shortly, which is understandable. It's similar to the thing that we saw in chapter 1 when you had binary features. The training and tests were very close. Okay, so you could have used the training as a proxy for for tests. So test and validation, you use the same. I hope you remember what the distinction was, but okay, so and this is in between. So what is GPT? So GPT is trying to model the interaction inter relations of words better, and there are a couple of innovations that led to this. So one innovation I think which is very interesting is that you can sort of linear word embedding. So that we talked about. So you had in the context of the bigram language model, you had a table which was let's say theta, and the rows after you apply the softmax with you probabilities. So you can think of this theta as an embedding of a word. So this is basically the logits that create the probability for the next word. So the conditional probability of observing the next word in one of the classes given the present word. So basically we can think of the embedding as so you embed the word into the continuous space via their logits on the next word. But you just get rid of this idea that these are maybe logits. You can think of just embedding words into the continuous space such that they encode some sort of information. And the advantage is that I can add two words. So for example, or here we have tokens, but let's say if you tokenize a lot of words, this could be maybe cat, this could be dog. And because I have vectors, I can add them up. So you can have a cat plus dog, or like two times cat plus one dog. So this might be a new like animal. Okay. And so there is interesting like operations that you can pass them through linear transformations or non-linear transformations, so you can operate on words like you operate on real vectors. And this is a pretty interesting idea. The other idea is that similarly, so these words are indices into some dictionary. Similarly, the position is also a discrete index. Okay, so I can also encode the position as a vector. So as I mentioned, for example, you have like hello here. In this case, tokens are words. Maybe this can be encoded as like maybe 31 and 0. 31 is the location of it in the dictionary, and 0 is the position. Okay. This one maybe, let's say in the dictionary, L is maybe 25, location 25, and this is the second position. This would be maybe, I don't know, these are not ordered, maybe, I don't know, 11 and 1. This would be again 25 and 3. This would be, for example, I don't know, 40 and 4. So we encode both of these indices by indexing into the corresponding tables. And so you encode the position. So if you have word WT, the value of the word is going to index into this token embedding table. The position is going to index into this position embedding table. And then we add them up. This is another interesting idea. And so I could have concatenated them, but they add them up. So in a sense, the position can also interact with the meaning. Okay, so for example, if later on I'll have one word whose representation is xt, the other one is like x prime t, then the representation encodes both the location and the word. So the location of the second one can interact with the meaning of the first one. So both the location and meaning can interact with location and meaning of each other word if I try to combine the words together. So in case any one of these words or tokens, in this case, tokens would be like characters in our case. But you can imagine you have more resources, you can try to tokenize at a higher level. And so each one gets a representation or embedding, and this embedding is what we operate on. So you get basically T, the size of the context, times the dimension of the embedding. So basically you get x1, x2, x. Okay, it would be x0, x1 up to xt minus 1, basically. So this is t-dimensional. This is 384. This is the embedding dimension. And what really happens is this corresponds to the back, which often I ignore. But yeah, we'll get to that. So the structure of the GPT is like you pass this through a bunch of blocks or layers, and at the end, so this layer norm is a form of normalization, which also appears inside these blocks. You can ignore this for now. And then at the end, there's a linear map that maps the 38, 384 to 65, which is like the dimension of our vocabulary. So you get a vector for each one of these. You get a vector 64. Now you can treat the 65. So at this point, you get like t by 65. This is the size of our dictionary. And the last one basically, so you can think of each one again as the logits, basically. Logits for the next word, and then we take the last one and the problem apply softmax and predict the probabilities of the next word. So these are basically giving me the logits of subsequent words. I want the word that comes after this. So we're going to get the softmax applied to the last row and predict. Okay. Sounds good. So the thing is, this embedding undergoes a very interesting transformation that encodes, like, you just encode all the information. So if you look at the code, you can see there's a token embedding table. The input code, if we apply the inputs to this token embedding table. So this goes, so index is batch size by key. So it's like, if you ignore the batch, you can ignore the batch here. So it would be T by C. C here is the embedding dimension. So you apply for each word, you get this table. Okay, and then you also apply, actually you get this data, the output of this. And then you apply, you have the position embedding table. You apply, this is basically 0 to T. So for each of these words, there's a bit of broadcasting going on here. So, yeah, so this will be really key latency. So 0 indexes into the table, and indexes into the table, you get basically the entire table just 0 indexes to this, one, and then you just copy this, and the one that you get from here, and then you add them up. Because of the broadcasting, so that this is gonna repeat for the batch size. But I mean, these minor issues we can ignore. You get the X, and then the X passes through these blocks. You can see that the blocks are defined here, right? So this is where the blocks are defined, and you can see it's a sequential application of this block object. So this block. So we create a block, and you will see like it has two parameters, and head, the number of heads. So we'll see what the number of heads is, and so you can, let's say not in the slides that I have, the number of heads is 3. So 384 by 3. So you create a bunch of these, let's say 3 of them, 6 of them, 12 of them. That's the number of layers. So the more you have, the deeper the deep learning is. So you have that, and then basically this is if you remember the sequential. Then I apply a sequential, like, so blocks would be a sequential object. When I apply it to X, it just sequentially applies it. It's just a composition of those functions. And so what you get is the option of here, and then there's the layer norm, the layer normalization, and then there's this LM head, which is really a linear map. Maps from the embedding dimension to the capsat, which is like 65. Okay, so that's basically the entire sort of GPT implementation here. And then you can see if I don't calculate loss, I just report like output the loss. So the losses that go there. The loss calculation is very similar to the Python language model. I can comment on later, but basically you're calculating the cross entropy between the logic at the particular position and the target and targets, which are basically the labels of the word after that. So this one is also not very difficult to understand. Is there any question about the general architecture of this? So we really need, like, at this point, the key format is this idea of word embedding and also position embedding. And then we need black boxes. Otherwise, you can see it's pretty simple. There was no name. Like 5 words. Yes.
How will one know that there will be 3 blocks?
How do you know it's 3 blocks? Okay, so in this code, these things are defined, and this is not a potentially nice way of doing it, but because it was educational, so n head is defined elsewhere in the code. So, for example, I said n head to be 3. So this is a global variable, right? But when you generate, you usually like pass these to the initializer or like the constructor.
I'm not asking in the code like as a concept. What happens when I add an extra block and then I delete a block?
What happens? So what kind of answer do you want to get? Well, I'll show you examples of 3 blocks and 6 blocks. So this is like the deep learning. It's like an engineer. So you play with this as another parameter, right? Whether it should be 3, 2, 10, 10,000. So how many you need is not an easy answer. Okay, but it's just another parameter of the model. How many heads? How many blocks do you need? Okay.
And each block is different from the other block.
It's exactly the same. This is exactly the same computation, but it has a bunch of parameters. And so these parameters are going to learn the gradient. So it's very similar to what we did with like MLP, multi-layer perceptron. We had this dense layer, and you can add like those codes that I showed you. You can have, I'll show you later. You can have one block on this layer, or you can have multiple blocks, and it gives you a different function. And then in practice, you would do, for example, you have a selection number of layers that you optimize over. So it's a hyperparameter selection problem.
So is it required that all the blocks should be same, or one can come up with different blocks?
So the one that there's no requirement. So this is like the design of a particular example. And so this is, so GPT is like something that, so the original paper that came up with, this is called generative trained transformer. Okay, so this transformer architecture is really what we're discussing here. And so the original paper is called "The Attention is All You Need." And I encourage you to read it after this lecture. You should be able to understand most of it. So this proposed this idea, okay? So you have these layers, and then you just repeat them a bunch of times, okay? And it's very similar in other areas of learning. You have a bunch of building blocks. Sometimes you like alternate a bunch of things, but oftentimes there is an architecture. When we say the architecture is like the design of this, right? So you could have completely designed it different. So I could like have a different kind of thing. This is not the best possible, but this is an example which has worked and sort of it's like the building sort of block of many of these current language models. Okay, whether you change this, yes, you can possibly change it and write a paper about it. It works better. You're just giving like one example, right? Sounds good. Any other questions? So the question of why you do this, in a lot of things in deep learning, there's no exact why. Okay, so people have like did like by trial and error, and things have worked out. Okay, and this is not necessarily the optimal thing to do. It's like at this point you're doing more on engineering, but I just want to dig into this so that you can see there's not much difficulty. It's not like these things are horribly difficult to understand. So this is basically what it does. It's a bunch of sequential operations, and these are parameters that you learn by gradient descent. Any other questions? So what is each one of these blocks? That's the structure of a block. Again, pretty simple. So I have this here to remind us that the things that we operate are these kinds of batch size by T form, and then you run the batch. This is just one. So we're just looking at these things in 3 by 84. So this is the next interesting idea. So this is called residual connection. Or you can call it residual channel or residual path. So this path passes through, if things are in there, it just passes through unchanged. The idea is that I'm going to just operate on it and then add it back to itself. The original idea was maybe to subtract. And so, for example, you have X, and it's in some model, and then operates, and then you get the residual, which is like this minus what I did. and then I'm going to model the residual. So for example, if you have your y and you try to predict it, first I predict it by a function f1x. This might not be as good. And then I'm going to look at the residual. I'm going to model this using another function f2x. And then if it's not as good, so in any case, we can see in regression, this is very natural. So you regress for the linear regression, you regress your x onto the covariance, and you have a residual. And you get the residual, if there is some pattern in it, then you can take the residual and then fit another model to it, and so on. So this idea is natural, and it's like it's a differential, but you just pick up the differentials, not have to like worry about that. So maybe like this takes on a lot of the issues in y, but there's some features that remain, and then the next guy comes in and takes up those features. So that's the idea, but really at this point, minus and plus don't really matter because this function can be plus or minus. So we can think of it this way as just doing just plus. You know, you can add minus, but you have linear mappings at the end, so the sign can be absorbed into f. So what you do is basically you add things back. And from an information perspective, it's very interesting because you these are like not like univariate functions. These are multivariate objects, or like objects in 4 dimensions. So you keep adding back, and potentially adding back in different subspaces. So this thing is going to have a lot of information stored in different subspaces. And each time that one of these operates on it, it extracts some of that information that does some processing and then writes it back. And so the next layer or the next block comes in and uses that information, does some operation on it, and then writes it back. Okay, so what this is doing is again a layer norm, and then this multi-head attention, which is at the heart of things, which we'll talk about. Then it just writes the same kind of dimension back in. And then the next operation in this block is the feed forward, what we call dense layer or multi-layer perceptron. This is the basic neural network. So you can see here, you have multi-head attention, number of heads and head size. We'll talk about that. And then a feed forward layer, which takes the embedding. So it's like this 384. This is 384. So math from 384 to 384, and then 2-layer normalization, which can ignore. So you basically apply the layer normalization, apply the this is called self-attention. So SA is self-attention, and then you add it back to X. You can see this residual idea. This is operating on it, and then adding back to X. I get X here, so I'm here at this point. And then apply layer norm, and then feed forward, and then add it back. So this procedure, and then we're done. Okay, so that's each one of these blocks. Okay. So now, what is the feed forward? The feed forward one is, we talked about last time, it's one of these neural networks that we've seen, which they call multi-layer perceptron. Okay, it's just a bunch of linear maps followed from linearity. In this case, one linear map goes from this dimension to 4 times that dimension, no linearity. And the linear map maps back to 384. And then there's this dropout, which we can talk about. It's like a form of regularization. So that layer norm and dropout are form of regularization we can ignore for now. And so this is your district here. This is very low right now. So this is a typical multi-layer perceptron, which is basically one hidden layer. So you have a hidden layer. I mentioned 4 times the input, and then you map it back to the output. Okay, so this does some nonlinear processing basically. So what is this? So that's the heart of the idea. Any questions? So let's dig into that. That multi-headed attention. So this is their innovation. So the idea is So this multi-headed efficient has multiple heads, as you can see here. And so the X comes in, you pass this X in parallel to all of these heads, and then you do some processing. What they do is that they map it usually to some lower dimension, each one. And then I concatenate, so let's say each one maps it to 64 dimensions, and then I concatenate them. So let's say in this case, maybe 192. And then I have to map it back to 384, then I'll usually do this by linear map. So if I don't want to like change dimensions from linear space to linear space, I have linear space mapping from 192 to 38. One dropout for just good measure, and then that's the multi-headed edge. So nothing fancy except that you have to understand what is going on in this head. Okay. So this you can also see it here very simply. So so this head is a list, module list of a bunch of heads, you can see. And you give it the head size here would be 64. And then there's a linear layer, which is this, and a dropout layer. So here what you'd see, you apply edge for every edge in the head. So for every head, basically apply edge to X, and then we concatenate the outputs along the last dimension. So last dimension would be this dimension, okay? And then pass it through. This projection is just a linear map. It's really not a projection, the opposite of projection, but it's called projection here, it's fine. And then this dropout, and then you get. So I just want you to like realize how easy it is to understand the code. So the code and this, if you go back and forth, nothing too fancy. And so oftentimes, this is designed so you divide this is dividable, so 384 I can divide by 3, so I get something such that I can calculate it 384 back. So usually this is not just forced it to be 64 here, so that you can see that potentially. Okay, so that's the multi-headed efficient. So what is each head doing? So is this sort of clear? Why do you do this? I really don't know, but this seems to work. Why do you need multiple palettes so you can change? So for example, you can have one head, and then don't do this part, remove this part, and see what happens. So this is what often people do, called the ablation study. So you move parts, change the number of heads, and yeah. Okay, so let's see what happens here. So let's now understand this. So this is the core. So you can see like nothing really strange going on, except maybe in the head. And then what does this head do that allows you to do this interesting language modeling? So here we jump back to something that we discussed very early on in chapter 2. So if we recall, we had this idea of similarity averaging. Okay. And what was the similarity averaging with the general non-parametric estimator of the regression function, where you had yi and xi as training, and if you wanted to calculate the expectation of y given x equal, writing it z used to be little x, but to avoid confusion, you want to approximate this regression function. If I had a similarity measure, I can measure the similarity of z to all of my training x's, then I would form this weighted average of yi's with the training x's that are similar. Okay, so you average all y's that are similar x to z. So we don't remember this. Okay, so and then Nadia Watson would come in if you use the translation invariant kernel. For example, if you use like a k that looks like, I forgot what I had, but like k0 xi minus z, this k0 could be the Gaussian kernel or so on. Okay, so that's good. A very simple idea is I can define this kernel like that. This is a more particular kernel. It's not translation invariant, but it's another similarity. So xi, this linear product of xi and z, e to the xi and z. So if z is similar to xi in the same direction, this product would be large. As the similarity would be large if orthogonal, this would be 0 could be actually the completely opposite, it could be smaller. Okay, so it could be 1 if they're orthogonal, it could be like less than 1 if they're in opposite directions. And something bigger than 1 if they are aligned. Okay, so it's a measure of similarity, right? So inner product measures similarity. So E is if I have two vectors, this is a form of similarity between the vectors, right? And E to the x and x prime is also a form of similarity. So you plug that in all the xi transpose z. And if you look at this, you remember there was a kind of weighted version of this we could write. So if you look at this, you can see that I'm forming this E to the xi transpose z, and then divided by the sum of all of them. So that's really a softmax operator. So this particular similarity averaging with this particular kernel can be easily written as this sort of ubiquity. So the YB is softmax, and this is a simple form. So if I have X, right, matrix written as X1 transpose up to Xn transpose times Z, that would give me all these inner products. Okay, so X1 transpose Z all the way to Xn transpose Z. So that's A to Z, and then if I apply softmax is a vector operation. Okay, so softmax would take this and produces weights. So you get E to the Xi transpose Z divided by the sum of all of them up to En transpose Z divided by the sum of all of them. And so these are the weights by which I'm going to average the Yi's. And so you get this weighted average of Yi's with this softmax. Okay, so it's a form of the estimated mean seen. And what I can do, for example, I can add a parameter in between. So for example, I can add a parameter, xi transpose, for example, I can have a theta parameter here. And then this parameter I can learn. So it could be like a learned similarity matrix. So another version of this would be I would say I would call it a parameterized attention. So it would be x theta z. So this defines a similarity, but also it allows me to have a parameter setting up to the bandwidth, but the full matrix here. So this defines a particular inner product. So this is the Euclidean inner product. This could make different directions different. So if you this gives you more flexibility, and it's like a mixture of this non-parametric idea and parametric idea. Okay, so if you remember, I don't know if you have seen it before, but there's this general form. So if A is a positive semi-definite matrix, this defines a general inner product. Okay. When A is the identity, this is usually the product, but depending on the eigenvectors of A, so you can measure similarity differently in different directions. You probably have seen this in the I think we talked about this. For linear regression, for example, the error that we got was something like that. And so this is an example of that. Basically normalizing that particular inner product and defining the signal. So we didn't talk too much about this, but in any case, so it's a way of changing the inner product. And so potentially allows you more flexibility. Okay, so this idea is what is at the heart of that hip business. Although they write data in a different fashion, I'll talk about that. But the main idea is that okay, we use this for scalar value xi and yi's, but this is a nonlinear operation. And it can work even if xi's are vectors, and I get just a nonlinear function of xi's. And so that's what happens in the head. So the idea is that for each, so this yi, you can think of it as let me show you. Is there any questions about this? So this idea people remember, and this I'm just saying there's a particular way of defining this kernel, and potentially you can add a parameter in between and learn that parameter as well. So this is okay, the heart of the this transformer idea. So let's ignore the code for now. So what happens is these vectors, like these representations, so these are Morgan vectors. So let's say I have 5 woods, then the mixing for 1 is for simplicity, t here is going to be 5, and each one is vector of this dimension in the image. Okay. And so I want to process this to sort of gather more information. What happens, their idea is, for example, let's say I want to process this word, and like x4. Okay. This is the word that's at location 4. This is its combined token and position embedding. Okay. What this word is going to do is going to pass this representation through a query. So this is a linear map that creates a linear, let's say called LQ of x4. So this is a parameter, the linear layout parameter, is a linear map. Produces a query, which is just a linear function of its position. And every one of the words also produces a key. So all the words pass their encoding through another linear operator, is a linear layer. And each one is translated to a key. So K1, K2, K3, that's also K4, K5. And then you compare this query query. So you compare the query of this to these keys via this numerical transformation. So basically these are my x's now. You can think of this as the x, and then I'm averaging a certain bunch of values, and these are like y's. And by taking inner products of the queries and keys, so basically I'm forming these. So this K matrix is like K1 transpose up to, let's say, K5. Apply to query. So this is like Q4 is like Z in the previous slide, and this is like X. And so this measures the similarity of the query to the keys, and then the softmax is going to relate which of these I'm going to use. And then on the average values, so these are y's, so the values are created from the same position. So that's the interesting idea. So each one of them pass its position through a linear map, which is, let's call this L value if you want. So this VI's are L value XI. So each position produces basically a value vector, a bunch of key vectors in a query. And you compare the query to each keys, and this defines the base that you want to average these values. Okay, so this is the final. The final formula is this, and you can see it. It's very similar to, so exactly this. If you think of the yi's as basically, this would be a query of let's actually, this is not the query. This is the value of I. This is the query of the particular one, and this is the K. Okay, so K is the key. This is the query. This is the value. So I'm just creating all of these from the position of this.
So this is a new architecture or expansion of the previous architecture?
So there is like the idea of attention is there in literature, but this particular form is what is in that paper. Oh, attention is all you need. But this idea, so attention is really so this word is going to attend only to a subset of these words for which these inner products are high. Okay. So that's the main idea I was like that. So the attention you can think of it as average. It's very old. That Barry Watson did something similar. But this particular mega, this is called self-attention because all of these are created from the same condition. And so it's not like so the actual paper has something called cross-attention. But this is a very interesting idea in the sense that the positions or these embeddings produce the things that you want. So each position has all the information that you need to query and then form the key and form the values. And then you're going to do this weighted averaging based on how close your query is close to the key of the other ones. So this language is from software engineering or databases. But you can think about it, it makes sense in the context of weighted averaging where similarities are formed. So if these are all identity matrices, what would happen is that only the words that have the same, like if this word is very similar to this, then the weight would be higher. So I'm going to use a higher sort of weight kind of averaging the values of this word. So, but more complicated things are happening here because of this linear maths here. And if you multiply this out, you would see that. So I have for example, I have an LQ here. So there's a linear mapping that maps x to this, and the linear mapping that maps x to these. And so if you make the sort of substitution, you get something like that. There's a parameter here which is like LQ transpose L key, something like that. So really, there's a parameter that attention is the factors for parameters in your models. But that's the whole story. So this is the main idea. Yeah.
Why is not a column?
So here when we're calculating, like say, this is this layer calculates a new embedding for each of these positions. I'm showing you what happens, for example, with X4. So this procedure is done, and you get a new embedding for X4. And these yi's here are the values that you predict. So these are like 64. So this is the head size. So this maps, let's say each one of these embeddings passes to this value, the linear map, and it's a 384 by 64 linear layer. It translates from this dimension to that dimension. Okay. So depending on the mathematics theory. So this is the core processing that's happening, and sort of mixes all every information. So there's this piece here that you can see I made the dead ends here. So when you process this, you're going to ignore everything after it. So you think of the language as sort of it's called causal self-attention, because this only will depend on these guys. So you set the weights of the words that come after it to 0 and also itself. So you don't want to contract it itself. You want to say at least. So what other words have to say about it? So they design like this, but there's no reason why necessarily future words. If you have future words here, then you're running into a problem at the end. You need futures to use predict the position of the first one. Because you always see the past, not the future. That's usually how it's. So this is like similarity averaging plus this idea of creating all this information from the embeddings themselves via linear map. Okay, so you have these positions, you create all the pieces that you need from this by different linear maps. Now these have parameters. So this layer has these parameters in the other. Like what kind of query should each word make, what kind of key they should generate and what kind of values they should have. Like, you can imagine each of these blocks will have different query key and value in your mapping, so they're extracting different information. Okay. Does that sort of make sense? It takes a while to sort of. This is the part of the report, which is important to let people easily go through it. So this, you can see there's a self key. Key is the like a linear map. So these are the linear mapping. So and an embedding head size, which is 64. There's another one which is query. There's another one which is value, and you pass the exit through the keys and queries. All of them create their own keys and queries, each one separately. And we like key by head size, and then you multiply this q times k transpose. Basically, this inner product, k times q, and then you mask out. This part is doing the call masking. So you mask everything that's after that, and then apply the soft max. So it produces these weights, and so there's a dropout for good measure, and then you apply. You apply the value as well. So this is the green part. The value, having to actually get the value, and then you, this is the nature part that gives you the average. So that's what is going on inside the head. Okay, sounds good. Let me look at it a little bit. So this operation happens for each one of these positions. So each position broadcasts one query, and also like their key and their value to everyone else. And everyone calculates their own representation. Okay. So each representation gets sort of updated via this process. So everyone shares information, and so you can think of the words talking to each other if you want, and deciding what our new representation is. And then the key idea, I think, is this kind of self-attention. So. There's in the original paper, if you look at, so this is sometimes called decoder only architecture. GPT is a decoder only architecture. If you look at the original paper, there's a cross attention, which is some of the attention comes from, so the attention calculation, some of it comes from the encoder. So something else also like affects these days. But this is based on the self. So this is easier to understand. Once you understand this, if you look at the original paper, you can see the cross attention idea. But that has been replaced with this very simple idea. This works. So the GPT is like the decoder only model. So this is the entire business here. Originally, it was developed for machine translation. So you had one language here, like one part of the world encoded the source language, the other one, the target language, and they had cross attention. But this turned out to work like even for translation. Okay, so that's it. So the entire thing we went through. So just going back, each of these blocks does the same thing. Each block operates on this summation of the token position embedding. So this is the excess, and the key thing here is in each block there's this multi-headed self-attention that updates these positions for the embeddings, and then there's this feed forward. In general, so you repeat these multiple times after each other, and all of them have parameters. So this multi-headed attention has a bunch of parameters for those key parameters. The layer also actually has parameters. You know, so this has a lot of parameters, right? So, and the inside the multi-headed attention, there's also a linear map to project. Whether you need it or not. If you have different dimensions, you want to move back to 384, and usually you're translating it into two different linear spaces of different dimensions. But you can design it so that this end is like 384. I think if I do like 128, 128, 128, 384. And so I don't need necessarily this, but this is also there in the architecture.
So what is there in that black box?
Yeah, this is what this is what in the black box. This is what is in the black box.
And what is the multi-headed the next slide?
So multi-headed is this part. That's the next slide, yes. I should have added the layer norm, but I'm just doing this. So you can ignore these bars, basically. That's if you want to be precise, there's the next slide is this entire thing. This entire operation, including so I should add a layer norm here. That would be that entire information. Okay. So layer norm, this is multi-headed attention. And then moves it back. So layer norm, multi-headed self-attention. So the head part is also an interesting idea, which is, I don't know if necessarily needed, but it works in parallel. You do it multiple times. So you do each one of these multiple times. So there's some operation going on in parallel, and then like sequentially. So this entire thing again is applied sequentially. So both in parallel and sequentially apply. So here in parallel, we calculate some information. You can calculate and move it like right back, and then you do the same process. But each layer gets their own parameters. So it quickly adds up. So if you imagine 384, for example, by 64, this is how much. So 64 by 84 is the dimension of all of these linear maps. So these are matrices and also biases. So 384 times 64, each one of them has this many parameters. And you have 3 of them, and you have multiple layers. There's also the before questions. So if you go through the code, you should be able to see all of this. So the idea is just again, a bunch of blocks that operate. There's a multi-headed self-attention and there's a feed forward in each block. And the multi-headed self-attention has multiple heads. Each head is doing something like that. Which is essentially like you can think of the similarity average that connects back to what we discussed in chapter 2. But there are some innovations. So there's this parameterization, effective parameterization. You don't have the x's and y's, so you're not operating on the input, you're operating on these latent embedded. And you create your own, basically, x and y. So what you want to and what you want to use as your features, x's, they all generated from your own representation. So this all like gets picked up by the model as you train.
The corresponding y of each x.
Yeah, so this is the corresponding y. And these are the x's basically.
Like a transformed version of it.
Yes, the x in the classification. I should have called this something else. Yeah. Right. So this is the x, the features in classification, and this is the y corresponding classification. The query and key are sort of playing the same role. And actually, I'm using dimension 64 here, but for example, the dimension here is different. But they often usually use a like math that the different dimensions have the same dimension, they take the inner product from the similarities. The 64 is the inside, the opposite side. Okay, so these are y's. So these are y's in classification. These are x's in classification. These two are x's. Okay. So in the interest of time, let's move on. So this is the result. So number of heads 6, number of layers 6, the embedding dimension 384, and the context being 256. The number of parameters is 10 million. You calculate how many parameters the model has. And the training loss goes like this, validation loss goes like this for 5,000. So these are the parameters that the original compatibility script has, and you can see the output. So this is much better. It's not visual, probably, it's not English, but it looks more like language. So for example, GPT-2, I believe, is like 175 billion parameters. Okay, and so if you go back to the code, you can check the number of tokens that we train on is like e to the 1 e to the 6 or 10 to the 6. So this has much more parameters than the total number of tokens that we have. And you can see a little bit of overfitting. I'll show you in the slide. that slightly negative validation is coming up. Okay. So training goes down, the validation, the flattens out and starts to go up. This is like sort of indicative of overfitting. Okay. This is my own sort of parameters. So 3 heads, 2 layers, the same number of contacts. So this is now 3.7 times 10 to the 3.7 million parameters. And it's similar, so similar final validation error. The quality you can judge for yourself. So it's still like not quite there. But, much better than the original. All gracious stores and this but yeah, so maybe this a little bit. So this is, you can see like doing evaluation of these is hard. So it's like the validation error is like similar. So even it's like slightly lower here. But molecular text is interesting. And then sorry. What will happen if I repeat this, like let it run for a very long time, this 6 by 6 or 10 million parameter model. So that's what you get. And you can see like your validation goes, like the training goes very down. Validation goes up back to 2.8. This is even worse than the background language model. But surprisingly, the quality of the text is not bad. So this is another surprise of the validation is bad. Training is really good. And the final output is good. So you run into a lot of interesting surprises. Okay, that's large language models for you. And if you have a GPU, you can train it yourself. So this takes a lot, like strong GPU. You can try it on your computer, but this could take a long time. With a GPU strong enough, you can try to train, and you can encode, like add more text and then try to do that, like change parameters and so on. Questions? Okay, so done with language models. So now in the last remaining 10 minutes, I'll try to talk about, so this overfitting that we saw, so that's an issue with all of these large models, right? So if you have a lot of parameters and sample sizes are smaller, so it's not clear the model really has this many free parameters, because in the end, the actual function might be not changing much if you change some of the parameters. So the actual dimension of the function space is not clear. But it seems like there is overfitting that happens. Overfitting is like a training, you fit very often training, but the validation, like on the test data, you're not necessarily doing that good. So imagine maybe this is the sweet spot, okay, where you have, so you can do what they call area determination, so you can stop, check the validation and see if it's turned off, then you stop. So this model might be better. It's debatable, and in this case, the output of the final version is interesting. So one of the ways that you can do with this is by regularization, which we've seen. So you've seen this regularization idea. And in particular, so let's combine the two ideas of trying to have a nonlinear model. Suppose I want to do linear regression. And usual linear regression, you assume you have a model yi, which is summation theta I xi, I from 1 to, let's say d, plus epsilon I. Oh, sorry, this would be, let's write it like that, f of xi plus epsilon I. Usually we assume that like f of x is theta transpose x. So this is a linear model, if you remember. And so, for example, in the concept of regression, univariate regression is just a line. In classification, would be just classification of linear boundaries. What if I want to have classification with nonlinear boundaries, or a nonlinear function, let's say in regression? The idea is that I can map this x to a new domain. So let's say x is one-dimensional. X is in R, but could be general. So I map it to, for example, 1, x, x2 up to x, k. Okay, so each one of my original features, which is one-dimensional, is now k-dimensional. And so if I now form a function like this, instead of x, I apply phi of x here, right? So in the feature space, so this is called the feature map. So in the feature space, I still have a linear. So a function is linear in these features, but in the original space, it will be non-linear. So this would give me a polynomial. You might have seen this before. And so I get xi to the, or x to the k. Should be k. Sorry, will be theta I xi, I from 0 to the k basically. Okay, so this is a polynomial function, which is non-linear, but I can fit it just like regression by just treating it as now I have a new set of features. Okay, so whenever you give me data, training data, xi, I'm going to pass it to phi of xi, and then call this xi tilde, let's say. Now I have a feature, so it used to be in R. Now I increase the dimension to rk, but that's fine. Now I have just yi's and xi's. Starting from yi's and xi's, now I have x tilde i's and yi's. Now I can do a linear regression, logistic regression, linear logistic regression in this domain, and it would be as if I'm doing nonlinear regression in the original domain. Okay, so you can do, for example, like nonlinear decision boundaries, and so on. So this doesn't have to be like this. It could be like a general basis function. So it would be like psi 0 of x, psi 1 of x. So this could be like an orthonormal basis. And so it gives you a very, so this could be, for example, sines, Fourier basis. This is a polynomial basis. You can get different polynomial bases or other bases of the space and so on. Okay, but this precision you can see in the dimension. And especially if you do it in multivariate, so x is already multivariate, forming a polynomial would create a lot of terms. So for example, if I have x is really x1, x2, even a degree 2 polynomial feature map would be, we would have how many? Like 1, x1, x2, x1, x2, x1 is squared, x2 is squared. Okay, and if I want to like a tree, polynomial tree, it would be much more. Okay, you can see if this original one is d-dimensional, we have a lot of terms. So I increase the dimension of the feature space, and then you run into issues because you have the same number of parameters here, and then this overfitting can occur easily. So originally, you have maybe, for example, I have 100 samples, and x is the dimension of x is 2 dimensions. But now I have 100 samples. The dimension of this new x is like what, 6, right? And if I do a polynomial to be 25, you can imagine that I have more parameters than samples, and I can easily. Okay, so then how do we deal with this? You can do the regularization. So you can add the regularization that tries to find within this huge function space now a set of parameters that best fits the model. So this precision with the problem with overfitting is that you increase the variance of the estimate. So you had like in the MSE, you had the bias variance decomposition. The variance would increase if you have like more parameters to fit to the training data. Because if you fit the noise pretty well, and the noise has variance, so the variance of your estimator goes up. So the idea is that you add, for example, a regularization, for example, L2 regularization, and in the context of regression, this would just be a regression. So you get some sort of expression like that, and then you can tune the lambda. So by choosing different lambdas, I get different parameters data, and I can sort of evaluate. So in practice, what you do is look at the test or validation blocks, and then you plug it as a function of lambda, and you find the lambda that minimizes it. So in this particular case for regression, we can do analysis. I don't have time to go over all the details, but I'm going to sketch the idea. So you can solve this linear regression. There's a closed form solution of this form, and the estimate of the function that we have is going to be here. I'm treating I'm ignoring the fact that so let's say phi of x is going to be called mu x. Okay, right. So my function is linear. So that's the linear regression estimate or prediction. So to make these assumptions, yi is at the start xi plus noise, and noise conditional on training is 0, meaning is sequence with identity. I'm not assuming that it's necessarily linear, but f hat is linear. And so what we can do is we can measure the performance in the so-called empirical norm. So how close f hat is to the star by looking at this is called the empirical L2 norm. So we get the deviation of functions on the training data squared and the average. So if you think of this is going to converge to some sort of an integral as the sample size grows of a random random x. So we'll work with this, and then you can write it in this form. This is not quite correct because we're not assuming the x start linear, but the next one is correct. And so you do the bias variance decomposition, you get an expression like that, where h is a matrix in terms of x. The psi is 1 over root n evaluations of f star at the training data. And so there's this bias term, and there's the noise, and then there's a cross term. And so this lambda is going to trade off the two. This is not very informative, but you can write things down more cleanly in the end if you do an eigen decomposition of this matrix. So this matrix is, so x is x1 transpose up to xn transpose. And if you look at 1 over n x transpose, it's like x, so the entries are xi transpose xj over n. So these are basically normalized similarities of the feature. So this is called the kernel matrix, RAM matrix, so the kernel matrix. So it turns out that the eigen decomposition of this matrix, so you form this kernel matrix, you look at the eigenvalues are, let's say, ui, the eigenvectors are ui, then this is the inner product of ui with that, this is the sampling operator. So this samples the function. So you can think of this as an approximation of the function. So you basically take the inner product of the star with the functions ui, the eigenvectors of this kernel matrix, and then so you can write the MSE in this very nice format, and you can easily see the trade-off. So for example, lambda is 0, the bias goes away. And you have all variance. But if you increase lambda, the bias goes down, right? So the bias is decreasing in lambda. So this term is going to go down, this term goes up. So it's very easy to see the effect of lambda, and then you can find minimums. So the function would have a minimum over lambda, which in general depends on how fast the eigenvalues decay and how fast these let's say alignment scores decay. So this tells you how much the function is aligned with eigenvectors of the kernel. And basically how much basically it aligns with the features that construct. So we don't have much time to go into it, but if the function aligns well with the polynomial basis, then this would be high early on, and so things would happen. If not, then a lot of these coefficients would be 0, and you would have an issue with the bias. But studying this would give you a lot of information, especially that the lambda equals 0 is not necessarily the best choice. So if you do this in an experiment, let's say I have a true function which is quadratic. So the original dimension is 1, and I have a quadratic function. So my, for example, true function is, I don't know, alpha 0 plus alpha 1x plus alpha 2x2. So that's sort of, with some noise, I have sort of these, so the x's and the y's. If I fit a degree 25 polynomial, 0 regularization, so we should have 0 regularization with that green curve. And if I do, for example, regularization 0.05, I get this green curve. Okay, so a limited regularization allows you to, although you're fitting a degree 5, degree 25 polynomial, you can see what we're fitting here. And you're fitting the noise very low, not necessarily function, but a little bit of regularization allows you to do a good job. And this is plotting the empirical MSE versus the theoretical line that I showed you, the theoretical formula. And you can see that the empirical one is just based on the one sample that we did. The theoretical one is sort of averages over multiple runs of the experiments where you generate, the function is the same, but you generate different y's. So given the same x, conditional on the same x. So this is, if you recall, average conditional on the training x's. So let's see. Average conditional on the training x's. So so this shows easily that like 0 regularization is not necessarily good, but the little that there's an optimal location, you get this by this is even from the training data, but you're going to see on the training data. But you can get the position using the validation very well. But this is showing the theory, and the practice sort of matches very well, and you can see that how it regularization allows you to fit these high dimensional models or too many parameters effectively. So you don't want this, but a little bit of regularization allows you to do that. And sort of in large language models, etc., there is a regularization of this form going on, which is, they call it weight decay. So effectively, if you do ridge regression, you just add a bit to the gradient. So you can easily see that you just shift the gradient a little bit. The effect of the gradient you can see here. But what they call weight decay is basically the loss, like lambda theta squared. And so when you take the gradient would be 2 lambda theta. So you just add the lambda theta to the gradients to the gradient step. And by controlling that, you can do a little bit of regularization. Okay, I'm going to stop here. Any questions, comments? That was a little fast, but hopefully we can check the chapter 7 more details. No questions? Thank you, guys. It was great teaching you, and good luck with the final. I'm going to